On April 4, 1943, a North American B-25C Mitchell bomber lost power in its port engine while conducting a training run over South Carolina. At 500 feet, the margin between controlled flight and catastrophic impact is measured in seconds. The aircraft was not at cruising altitude, where a pilot has the luxury of trading height for speed or time to troubleshoot a fuel feed issue. It was low and fast, practicing a technique known as skip bombing, where the aircraft approaches the water surface to release ordnance that ricochets into the side of a naval target. When the 18-cylinder radial engine on the left wing failed, the sudden loss of thrust created an immediate and violent yaw. The physics of asymmetric thrust at low altitude and high power are unforgiving. The operating engine on the right wing continued to generate nearly 1,700 horsepower, pushing the right side of the aircraft forward while the dead left wing dragged the airframe back. The pilot faced a binary decision set dictated by velocity and altitude. If he reduced power on the good engine to stop the turn, the aircraft would stall and drop out of the sky before reaching the shore. If he maximized power to maintain altitude, the torque would roll the aircraft onto its back. The crew braced for the inevitable intersection with the surface. The pilot managed to keep the wings relatively level, but the aircraft had to trade its remaining energy for a controlled collision with the lake. The B-25 hit the water in a tail-low attitude. The structural violence of a ditching event is defined by the density difference between air and water. Air compresses, but water at speed acts like a solid impact barrier. When the starboard propeller struck the surface, the resistance was instantaneous. The rotating mass of the propeller and the radial engine encountered a medium 800 times denser than the air it had been pulling seconds earlier. The torque loads exceeded the shear strength of the engine mounts. The entire starboard engine assembly tore free from the wing structure. This mechanical failure likely saved the fuselage from twisting apart. By shedding the heavy engine and its gyroscopic forces, the airframe dissipated a massive amount of kinetic energy without transferring that shock load into the cockpit section. The bomber skidded to a stop, floating briefly on trapped air and residual buoyancy in the structure. The crew exited the aircraft quickly. In the forensic reconstruction of the event, the evidence of their escape remains locked in the airframe. The pilot's side-sliding window was found secured in the open position. This is not a dramatic interpretation, but a mechanical fact verified by the position of the latch. It confirms that the airframe remained afloat long enough for the crew to execute a disciplined egress before the vents and seams took on water. The aircraft then began its final descent, settling 150 feet down to the lake bed. It landed upright on its tricycle landing gear as if parked on a runway obscured by darkness. For the next 62 years, the bomber sat in the cold, dark water of Lake Murray, known locally, rarely fixed to precise coordinates. Between 1943 and 2005, it shifted from a military loss to an archaeological artifact, but any attempt to touch it carried a second constraint. The lake is a drinking water reservoir, so permitting and method were as critical as engineering. Finding the aircraft required a systematic side-scan sonar search, using sound to separate natural contours from the straight geometry of manufactured metal. When the return finally resolved into a target, the silhouette was unmistakable. A 67-foot wingspan, twin vertical stabilizers, and a damage signature consistent with the ditching. The starboard engine absent while the port engine remained attached, pinning the left side down. This asymmetric weight distribution on the bottom meant the wreck was not just sitting in the mud, it was settling into it. The lake floor at that depth consists of a thick layer of ultrafine silt. Over 6 decades, this silt acted less like soil and more like a viscous fluid that slowly solidified around the aluminum. The fuselage did not just rest on the bottom, it became integrated into the sediment. This created a significant engineering problem for any potential recovery. The aircraft was no longer just a 20,000-pound assembly of metal. It was a structure glued to the earth by hydrostatic pressure and suction. The objective was clear, but the method was restricted. The goal was to recover the airframe intact for preservation and display at the Southern Museum of Flight. However, the decision to disturb a site that has been static for half a century is not taken lightly. The structural integrity of 1940s aluminum alloy after 60 years of saturation is an unknown variable until the moment you try to lift it. The skin might look perfect, but the internal stringers and bulkheads could be compromised by hidden corrosion. Identifying the specific aircraft was the first forensic requirement. The B-25C variant is distinct from the later and more common J models. It carried a different nose configuration and different exhaust stacks. But positive identification required more than a silhouette. It required reading the data plate or verifying the serial number 4112634. This number confirms the identity of the machine and links it to the specific crew that escaped that April afternoon. It distinguishes this airframe from other losses in the region, preventing the historical confusion that often plagues aviation archaeology. The challenge facing the recovery team was not just the weight of the plane, it was the fragility of the artifact. You cannot simply wrap a cable around the tail and pull. The aluminum skin is less than 0.04 of an inch thick in places. Point loads from a chain or a cable would slice through the fuselage like a wire through cheese. The lift requires a distribution of force that mirrors the way the aircraft was designed to carry loads in flight. But instead of lift generated by air moving over the wings, the force must be applied mechanically from above while the mud pulls from below. The aircraft rests in a state of equilibrium. It has equalized with the pressure and the temperature of the water. Disturbing that equilibrium introduces energy into a system that has been dormant since the Roosevelt administration. The decision to recover is a decision to expose the airframe to a new set of risks. The transition from the stability of the bottom to the violence of the surface is the most dangerous phase of the entire operation. But before the team could even plan the lift, they had to understand exactly what the water had done to the metal. The environment of Lake Murray is not passive, it is a chemical bath that has been working on the airframe for 22,000 days. 150 feet of water creates a boundary that separates the surface world from the preservation zone below. At this depth, the environment is defined by 3 hard numbers. The pressure is 4.5 times greater than at sea level. The temperature holds steady near 50 degrees Fahrenheit regardless of the season. The visibility is often less than 0.5 inches. This is not a passive void. It is a pressurized cold storage locker that has held the Mitchell bomber in a state of suspended animation for 62 years. Assessing conditions starts with hydrostatic pressure and equalization. When the aircraft sank in 1943, water drove into every void, through the open pilot's window, the nose wheel well, and the fuselage compartments, until internal and external pressure matched. That equalization was the preservation mechanism. Had major volumes remained sealed, the differential, nearly 66 pounds per square inch at this depth, could have crushed thin sections inward. Instead, the structure stayed geometrically true because the pressure balance removed the hull-crush load case. Lake Murray's freshwater chemistry removed the ocean's most aggressive accelerator, chlorides. At depth, the wreck also sat below the thermocline and often below the photic zone, reducing sunlight-driven growth and eliminating heavy, encrusting marine life. But the decisive preservative was burial. The bomber settled into ultrafine silt that wrapped the lower fuselage, wings, and nacelles and formed an oxygen-starved anaerobic seal. With oxygen limited, the corrosion cycle slowed dramatically, pausing much of the aluminum's chemical aging while the aircraft remained entombed. This creates a visual paradox that is deceptive to the recovery engineer. When divers wipe away the layer of silt, the olive drab paint underneath appears factory fresh. The United States Army Air Force's insignia is vibrant. The yellow stenciling on the side of the nose is legible. This is the mud seal effect. It creates the illusion that the aircraft is as strong as the day it left the assembly line. But this visual perfection hides the structural reality. The aluminum skin is preserved, but the materials that bind the aircraft together are not. The darkness at 150 feet masks the scale of the challenge. A diver descending to the site enters a world of total blackness. High-intensity lights cut through the water, but the beam simply reflects off the suspended particulate matter, creating a wall of white fog. You cannot see the entire aircraft. You can only see a section of rivet line or a tire tread or a gun turret. This forces the survey team to build a mental model of the wreck one piece at a time. They must rely on touch as much as sight. The lakebed posed a mechanical threat distinct from gravity. The silt did not merely support the aircraft, it bonded to it. With so much surface area in contact, the breakout would be defined by one controlled step. Collapse the silt seal without spiking loads high enough to tear 60-year-old aluminum before the mud released. The preservation strategy for this recovery is defined by these environmental conditions. In many recoveries, the goal is restoration to flight status, which involves replacing 80% of the metal. Here, the goal is conservation. The objective is to stabilize the artifact exactly as it is preserving the original 1943 materials. This means the corrosion must be arrested, not reversed. The silt that has protected the plane is also the greatest danger during the extraction. It adds thousands of pounds of parasitic weight and resistance. While the anaerobic mud saved the aluminum skin, it could not protect everything. The aircraft is a complex machine made of mixed materials. Rubber hoses, fabric control surfaces, and steel cables react differently to long-term submersion. The impact dynamics discussed previously tore the right engine off, but the water has been slowly disassembling the softer components for decades. The fabric that covered the rudders and elevators has rotted away, leaving only the skeletal aluminum frames. This biological decay is selective. It eats the organic materials and leaves the metal. The lake preserves surfaces while quietly degrading what you cannot see. As the team prepared to disturb the equilibrium, they were dealing with a waterlogged structure, heavy with embedded silt, and held together by rivets that had not carried real load since the middle of the war. The next step was no longer description. It was measurement, hands on metal in the dark. The transition from a sonar shadow to a confirmed identity requires physical contact. Side-scan sonar provided the location and the general orientation of the target, but it could not assess the structural health of the aluminum. To build a recovery plan, the team needed to verify exactly what was resting in the silt. This phase of the operation moved from remote sensing to tactile survey. Divers descended into the darkness to touch the metal that had been lost since 1943. The primary objective of the survey was to confirm variant and condition. The B-25C carries features that separate it from later models, and one high-value verification point was the lower gun turret. Many surviving airframes had the retractable ventral turret removed over the years, but here divers found it retracted and intact, hardware consistent with the documented configuration for serial number 4112634. With the serial, the wreck could be tied to the 376th Bomb Squadron, 309th Bomb Group, and anchored unambiguously in the historical record. However, the survey revealed a hidden threat that sonar could not detect. While the exterior skin appeared preserved by the anaerobic mud, the internal components were fighting a different battle. An aircraft is an assembly of thousands of parts made from different metals. Aluminum makes up the skin and ribs, but steel is used for control cables, bolts, and pulleys. When these dissimilar metals are submerged in water, they create a galvanic couple. Even in freshwater, the airframe effectively becomes a massive battery. This is the physics of galvanic corrosion. It is an electrochemical process where one metal acts as an anode and the other as a cathode. Electrons flow between them, causing one material to degrade while the other remains stable. In the case of the Lake Murray bomber, the interaction between the stainless steel control cables and the aluminum alloy pulleys created localized corrosion cells. This reaction does not happen overnight. It is a slow, relentless decay that occurs over decades. The survey confirmed that the control cables running through the fuselage were likely compromised or fused to their guides. The movable surfaces of the aircraft were no longer movable. The mechanical linkages that once allowed a pilot to steer the bomber were now chemically welded shut or disintegrated. This reality changed the engineering calculus for the lift. If the internal steel structure was weakened, the airframe could not be treated as a rigid beam. The lift points designed by North American Aviation in the 1940s were intended for a factory-fresh aircraft with full structural integrity. Using those same hard points 62 years later would invite failure. A standard crane lift often relies on attaching cables to specific reinforced lugs. If the bolts holding those lugs were victims of galvanic corrosion, applying 20 tons of tension would rip them out of the aluminum skin. The survey also highlighted the difference between the dry weight and the wet weight of the recovery target. The empty weight of a standard B-25C is approximately 20,000 pounds, but this aircraft was not empty. It was filled with water and impacted with mud. Every interior compartment from the bomb bay to the tail section was carrying additional mass. The weight calculation had to account not just for the aluminum and steel, but for the enclosed volume of water that would be lifted along with it. The divers also examined the wings to understand the lifting geometry. The B-25 has a distinctive gull wing shape, with the outer wing panels carrying a slight dihedral or upward angle. Preserving this geometry was critical. If the lift applied force in the wrong vector, it would buckle the spars. The survey confirmed that the wing roots where the wings join the fuselage were the strongest remaining points of the structure. The spars here were deep and reinforced, capable of taking a load that smaller ribs could not. Further visual inspection of the tail section utilized the decay of softer materials to the team's advantage. The fabric that originally covered the rudders and elevators had rotted away decades ago. This left the aluminum frames exposed like a skeleton. While this was a loss of original material, it allowed divers to inspect the internal riveting and spar construction of the control surfaces without removing any panels. It verified that the metal structure of the tail was intact even if the skin was gone. The identification was absolute. The survey matched the serial number and the unique damage profile of the missing starboard engine. There was no ambiguity. This was the aircraft that lost power in April 1943. But the survey also delivered a warning. The aircraft was fragile. It was a shell of preserved aluminum hiding a compromised steel nervous system. It could not be flown to the surface. It had to be cradled. The structural survey dictated that the recovery team could not use standard salvage techniques. They had to design a method that would respect the weakened state of the galvanic couples and the massive suction of the silt. The aircraft was ready to be moved, but the standard tools of the trade were too violent for the task. The operational plan for raising the Mitchell bomber was dictated by a single overriding constraint that had nothing to do with aviation. Lake Murray is a primary source of drinking water for the region. This designation imposes strict environmental controls on any industrial activity conducted on the water. A standard salvage operation typically employs a crane barge driven by high-pressure hydraulic systems. Hydraulic fluid is effective for heavy lifting, but it presents a catastrophic risk in a reservoir. A single burst hose could release gallons of oil into the water supply, triggering an environmental disaster and immediate shutdown of the project. The recovery team had to design a lift system that generated 20 tons of vertical force without using a drop of hydraulic fluid. The solution was to replace fluid dynamics with pneumatics. The team engineered a custom lifting platform that utilized air pressure instead of oil pressure. On the surface barge, a series of heavy-duty pneumatic jacks and winches were installed. These machines are powered by compressed air, which is clean and environmentally neutral. If a line ruptures, the only thing released into the lake is bubbles. This decision traded speed for safety. Pneumatic systems often lack the smooth precision of hydraulics, but they provided the necessary force while strictly adhering to the permit requirements. Below the surface, the rigging design had to solve the problem of structural fragility. You cannot lift a 60-year-old aircraft by its propeller hubs or landing gear struts. The load must be applied to the strongest remaining part of the airframe. The survey identified the wing roots, where the wings join the fuselage, as the primary load paths. These sections contain the heavy main spars designed to carry the weight of the aircraft in flight. However, simply wrapping a strap around the wings would crush the leading and trailing edges inward. To prevent this, the team fabricated a specialized spreader bar. This was not a simple steel beam. It was a custom-engineered frame built to match the exact dihedral angle of the B-25 wings. The geometry of the spreader bar ensured that the lifting straps hung perfectly vertical. This directed the lift force straight up into the spars rather than squeezing the fuselage sideways. Wide nylon straps were positioned carefully under the wing roots, distributing the pressure over a broad surface area to avoid slicing through the preserved aluminum skin. With the rigging secured, the operation moved to the most physically demanding phase, known as the breakout. The aircraft was not just resting on the bottom, it was embedded in the silt. The physics of this interaction creates a phenomenon known as stiction or static friction, amplified by suction. The mud had displaced the water around the lower hull, creating a seal. To lift the plane, the winch had to overcome the weight of the aircraft, plus the weight of the water inside it, plus the resistance of this vacuum seal. The engineering estimate for the lift load was approximately 40,000 pounds. This figure included the 20,000-pound dry weight of the airframe and the additional mass of the water and mud. The pneumatic winches began to apply tension slowly. This was not a rapid extraction. The goal was to increase the upward pull incrementally, allowing water to seep into the mud seal and equalize the pressure. If the team pulled too fast, the suction would hold the fuselage down while the wings were pulled up, potentially ripping the aircraft apart at the joints. The process required patience and discipline. The tension was increased pound by pound. The straps stretched tight. The spreader bar took the load. On the bottom, the aircraft began to complain. The sound of metal shifting in the mud transmitted through the water. Then the seal broke. The suction released its grip and the bomber popped free from the sediment. For the first time in 6 decades, the landing gear left the lake bed. Once the breakout force was overcome, the physics changed. The aircraft was no longer fighting the earth. It was suspended in the water column. The pneumatic system transitioned from breaking the seal to managing a controlled ascent. The bomber was raised slowly to allow the pressure inside the fuselage to equalize with the decreasing depth. As it rose, the external water pressure dropped and the air trapped inside the structure expanded. The team had to manage the ascent rate to prevent any sealed compartments from overpressurizing and bursting. The lift continued until the aircraft hung just below the surface barge. It was off the bottom and secure in the rigging, but it was still submerged. The successful breakout proved that the spreader bar geometry was correct and the pneumatic jacks were sufficient. The aircraft was intact. But the physics of the recovery were about to invert. As long as the plane remained underwater, it was supported by buoyancy. The moment it broke the surface, that support would vanish, leaving the weakened structure to carry its own water-filled weight. The most critical minute in a 62-year recovery is the surface interface. Underwater buoyancy and external pressure support the skin, and the water inside the fuselage is largely weight neutral relative to the surrounding lake. The moment the aircraft breaches the surface, that support collapses and the trapped water becomes a hanging load. Freshwater weighs roughly 8.3 pounds per gallon, and the B-25's fuselage can behave like a containment vessel. Lift it clean without preparation, and the water mass can exceed what weakened riveted joints and wing root structure can tolerate, inviting a tearaway failure even if the spreader bar holds. So the team raised the bomber until the dorsal turret and the top of the fuselage just broke the surface, then stopped in a controlled transition zone. The pneumatic winches held the load steady while the next phase began. Pumped down the internal fluid before the airframe had to carry it in a 1G world. Pumps were lowered into the open crew hatches and the fuselage compartments. The volume of fluid inside was significant. The team had to pump out nearly 800 gallons of liquid to reduce the hanging weight to a safe margin. This was not just lake water. As the water level dropped, the smell of high-octane aviation fuel drifted across the recovery barge. The fuel tanks inside the wings had held their integrity for 6 decades. The mixture being pumped out was a cocktail of 1943 gasoline and lake water. This introduced a hazardous materials constraint to the structural problem. The vapors were flammable and the fluid had to be contained to prevent environmental contamination of the reservoir. This pumping process is a race against structural fatigue. As the water level inside drops, the airframe becomes lighter, and the stress on the lifting straps decreases. But the external water support is also vanishing. The hull is transitioning from being supported by the lake to being supported entirely by the aluminum skin and the spreader bar. The custom geometry of the spreader bar discussed earlier now performed its primary function. It kept the lifting straps strictly vertical, preventing the crushing force that would otherwise fold the fuselage inward as the internal pressure support was removed. The pump down took hours. The team monitored the waterline on the fuselage. As the internal weight decreased, the pneumatic winches raised the aircraft inch by inch. The nose section emerged, revealing the glass bombardier enclosure. Then the cockpit windows broke the surface. The water drained from the drain holes and the pumped sections, lightening the load until the aircraft reached its dry weight of approximately 20,000 pounds. The decision to pause and pump was the pivot point that ensured success. Had the team attempted a continuous lift, the structural failure would have been mathematically guaranteed. By respecting the physics of the surface transition, they converted a dynamic risk into a controlled sequence. The aircraft was finally lifted clear of the water. It hung suspended over the deck of the recovery barge, a dark green shape dripping with the silt of the lake bottom. The transition to the barge deck required one final precise movement. The aircraft had to be lowered onto a prepared cradle. This cradle was built to support the fuselage at its bulkheads, the strong points of the internal structure. The landing gear was down, but it could not be trusted to support the weight of the aircraft after 60 years of corrosion. The hydraulic seals in the struts were likely gone, and the oleo struts might collapse under load. The airframe was lowered gently onto the cradle, transferring the weight from the nylon straps to the steel support frame. The outcome path was locked. The aircraft was surface side. It was intact. The fuselage had not hogged or sagged. The wings were straight. The starboard engine was missing as expected, but the port engine was secure. The preservation of the aluminum skin was confirmed to be as remarkable as the initial surveys suggested. The mud had done its work. The paint was not just visible, it was vibrant. However, the successful recovery of the airframe brought an immediate operational consequence. This was a warplane on a combat training mission. It was not flying empty. As the water drained away and the interior compartments became accessible, the reality of the cargo became the primary focus. The aircraft was still armed. The machine guns were mounted in their stations. The ammunition boxes were potentially full. The recovery operation had succeeded in retrieving the hardware, but in doing so, it had brought live ordnance into a public space. The engineering challenge of the lift was finished, but the legal and safety challenge of the legacy was just beginning. The aircraft was no longer a wreck at the bottom of a lake. It was a weapon on the deck of a barge. When the Mitchell bomber settled onto the deck of the recovery barge, the operation shifted from a salvage mandate to a law enforcement protocol. The presence of military ordnance on a civilian vessel creates a specific jurisdiction problem. The aircraft was equipped with 50 caliber Browning machine guns. After 62 years underwater, the mechanical condition of these weapons was unknown, but the legal status was binary. They were classified as live firearms. The recovery team had coordinated with the Bureau of Alcohol, Tobacco, Firearms, and Explosives prior to the lift. Federal agents were on site not to admire the aircraft, but to secure the weaponry. The guns were removed from the turrets and the nose compartment. Despite the decades of immersion, the stainless steel components of the receivers were often found to be functional. The ammunition feeds were inspected. The preservation qualities of the anaerobic mud that saved the aluminum skin had also potentially preserved the powder charges in the ammunition. The risk of unexploded ordnance, or UXO, is a standard constraint in military recovery, but it is rarely encountered in a public drinking water reservoir. The securement of these weapons marked the official transition of custody from the lake to the museum. With the hazards neutralized, the logistics of transport became the primary engineering challenge. A B-25 has a wingspan of over 67 feet. It cannot be transported down a highway in one piece. In many recovery operations, particularly those involving wrecks that have suffered severe structural damage, the airframe is cut into manageable sections using torches or saws. This technique destroys historical fabric to facilitate movement. For serial number 4112634, the team chose a different path. They utilized the original manufacturing brakes designed by North American Aviation in 1941. The B-25 was built in sub-assemblies that were bolted together. Because the corrosion had been arrested by the silt, the team attempted to unbolt the wings from the fuselage rather than cutting them. Using penetrating oil and patience, they worked on fasteners that had been tightened during the Roosevelt administration. Remarkably, many of the bolts turned. The aircraft was disassembled into its factory components: the fuselage, the wing panels, and the tail section. This approach respected the integrity of the artifact, avoiding the irreversible damage of the cutting torch. The aircraft was transported to the Southern Museum of Flight in Birmingham, Alabama. Here, the curators faced a philosophical decision that defines modern aviation archaeology. The choice was between restoration and conservation. Restoration implies returning the aircraft to a specific point in its history, usually its factory new condition. This requires stripping the paint, removing the corrosion, replacing damaged metal, and often manufacturing new parts to replace missing ones. It erases the evidence of the crash and the evidence of the time spent underwater to create a pristine representation of the type. Conservation takes the opposite approach. The goal of conservation is to stabilize the object and arrest any further decay while preserving the history of its life, including the crash and the recovery. The museum chose conservation. They decided not to restore the Lake Murray B-25 to flight status or static perfection. Instead, they focused on stopping the chemical processes that were eating the metal. The airframe was cleaned to remove the bulk of the biological matter and the reactive chlorides, but the traces of the lake were allowed to remain. The silt that had accumulated in the deep crevices of the cockpit and the bomb bay was left in place. The corrosion on the steel parts was treated with inhibitors to stop the active rust, but the pitted surface was not filled or polished. The fabric control surfaces, which had rotted away, were not replaced with modern Dacron. The aluminum skeleton of the tail was left exposed, revealing the internal architecture of the World War II design. This decision transforms the aircraft from a generic display into a specific historical document. A restored B-25 looks like every other B-25. This aircraft looks like a survivor of a ditching and a 60-year submersion. The open pilot's window remains open. The missing starboard engine remains missing. The dents and buckles in the lower fuselage telling the story of the impact with the water are preserved as evidence of the pilot's final seconds of control. The technical success of the recovery is measured not just by the fact that the plane is dry, but by the fidelity of the preservation. The pneumatic lift, the spreader bar geometry, and the controlled pumping sequence delivered the airframe to the laboratory without adding new damage. The identification is absolute. The serial number connects the metal to the names of the crew who swam away in April 1943. Today, the aircraft is displayed in a way that allows visitors to see the complexity of the machine and the power of the environment that held it. It is a study in material science as much as it is a study in history. It demonstrates how aluminum resists water, how steel surrenders to it, and how a sudden loss of energy at 500 feet can be frozen in time. The recovery of the Lake Murray B-25 closed the gap between the event and the evidence. The bomber is no longer a legend in the mud. It is a verified physical reality standing on its own landing gear, stable and secure.